Hi everyone, I'm Ryan Fisher from Christopher Newport University. I work in LIGO, and this talk is from LIGO, Virgo, Kagra, Chime. All of those have contributed to things in this talk, so I'm great to everybody. I also start at some very basic stuff, but I'll go really fast. Students in the audience, like wave at me if you want me to slow down, okay? So I'm going to go very fast at the beginning. Okay, so what do we do with LIGO? We're observing gravitational waves, right? We just heard about these. We have massive objects moving nearly the speed of light. We need that to actually detect things. So we have ripples in space-time. This is what I focus on, just to give you a sense of my expertise. I focus on compact binary coalescences associated with fast radio bursts for this talk. That's my part, but I'll talk about all the things we do. Okay, what it actually does is stretch and squish space-time. Okay, so it's stretching and squishing space-time. That requires L-shaped arms in our detectors, right? One arm is going to get stretched while the other one is squished, vice versa as the gravitational wave goes through. Bigger detectors mean better sensitivity because we're measuring strain, which is change in length over length. If we have a bigger length, that means the change in length we can measure can be bigger. Okay, very simply put. All right, so sensitivity then from putting those things together. So 01 through 05, we're in 04 right now, so observing on 4. It's been split into 3 parts, so we're in 04C now. And that detection range is 160 to 190 megaparsecs for binary neutron star merger. Okay, and this is made up of a noise of many things. Down here, a lot of this is seismic noise and noise from the ground. A lot of noise up here is quantum noise effects, but it's a combined noise curve from all those things. But yeah, we're operating here in 04, which is better than ever before. But you see in 05, which is a few years out, maybe almost double the distance, right? So that gives you a sense of scales. And then time scales, for people who aren't familiar, we are right here, right? So this is 2025, we're right here. So we're right before a small commissioning break now, which has been added to our run. There's going to be a small commissioning break, and then we will observe again until basically October for this 04 run. The sensitivity isn't supposed to go up a lot. This is to deal with a whole bunch of different things. But Virgo is also operating and taking a similar small break, and so their sensitivity might go up a bit. Is the goal, I think, of that break. It's one of the things I think. I'm not in Virgo. We have a Virgo expert in the audience, and she can tell you more if you'd like to. And then Kagra is getting data at the same time. The interesting thing is here you see the original plan was 160 and 190, and it went down. But then if you go back here, well, I'll show you in a second what that is. I want to explain this before I show you the next slide. So what we're doing in our search, the one that I'm talking about primarily, which is PyGRB, is this match filter search, right? You know the waveform because you know the compact binary coalescence. It's 2 massive objects orbiting in, and so you should have this oscillation that then grows in amplitude until and the frequency also grows. And so you match it, and I'll play this again if you haven't seen this, just using match filter SNR. You're just sliding the waveform against the data for the times that you're looking for, although we're restricting our times because we're looking around a specific event. And then you get out an effectively enhanced estimate. Like I said, I'm going to go fast at the beginning. So this is where we're at now. This I just pulled down from the WASC is our open science website, so you can see this yourself if you want to go to it. I just pulled this down right before I made the talk. And so we have about 170 megaparsecs range on Livingston. That's for a binary neutron star merger, right, on average. And then Hanford's a little lower, and Virgo's down here, right? And so, right. So I'll just kind of skip over that. With the low detection range of Virgo, it's actually pretty good, but it does limit our ability to localize a little bit, but actually that's good enough to get pretty good localizations that you might see in the things that have gone out. Okay, unmodeled transient searches are the other flip side of the coin that we also do. And so this is just taking time frequency maps as one example of how to do this. You take the time frequency map, and you look for excess energy, and you look for clustered excess energy. And if it's clustered enough, it stands up against the background. And you compare the energy of your cluster versus the energy of the other clusters you find, and look at the evidence for detection. You can also use the coincidence or the coherence between the detectors, right? So if you actually have coherent data between the detectors, because you're looking at a certain sky point, you can use the time offsets of where that data should arrive on the 2 detectors. Use the coherence of that, and you can use that to reject background signals and get better weighting on your actual detection signal. And then this is kind of really important later. So on the right, you'll see the time frequency map. I don't think there's any sound because we can't get the sound to work when we try. But on the right, you'll see the time frequency map of our first detection. And again, what it should look like is a swoop. So it goes whoop, right? Okay, so it should look like a swoop that goes up. And now this is two black holes, so it's quite fast. If you have binary neutron stars, it's much slower, or neutron star black hole, it'll be slower than this. But if you look at some of our noise artifacts, unfortunately, this is what we call blip, and we have a lot of these. They ramp up in a similar fashion on a short time scale. So these, so especially the highest mass black holes can look like these, or rather the bad thing is that these can look like high mass black holes. And also the upswings of things like this, which was a whistle noise. This was actually a radio frequency oscillator that was messing up. But anyway, so the idea is that this kind of upswing on these arcs can look like signals. So this is the kind of thing that we really have to deal with. Most of the time, this is what contaminates our data the worst, and much more so than just this, right? So this is ideal, and then we add all that on top, right? So that's the idea. Okay. So go back to this guy. I did hear a sound there. Okay, so I got a sound for a second, but that's okay. So then this is what it looks like when you just take a day. No, this is 6 hours. Of all the gravitational wave triggers. Yeah, they're all gravitational waves. No, they're not all gravitational waves. They're mostly glitches that I just showed you, right? They're mostly glitches. And we're pretty good at saying which ones are glitches and not gravitational waves now after looking at millions of glitches, essentially, is the way it works. So that's the idea. But they do look sort of chirpy. All right, one last thing on there. So this is a little old now, but this is all the gravitational wave detections up to a certain point, and it's showing mass on the y-axis, and showing the two things that have combined in the final result, right? And so the ones we're looking at are all in here, because these are the things that might involve a neutron star, right? So anything above here, black hole, though now we heard today maybe some black hole stuff might be more interesting. Up until now, we're not considering black hole for anything to do with EM bright, right? So anything with electromagnetically bright. All right, so this is the big picture model. I'm just using GW170817 as the pictures, just so it's easy. You have some progenitor. The progenitor produces our gravitational wave and some other things, depending on your model up there and depending on the kind of models we sold today. It hits your telescope in radio, or it hits your gamma ray detector in gamma ray burst, and hits LIGO at the same time. And the key is that we need to have some way of communicating fast, right? That's one of the key things, is that we communicate fast. And so we have lots of different ways to do that, and then there can be follow-up, like there was for 17817. And then the follow-up produces some really awesome stuff, right? I mean, that's the goal, right? That's the goal, and we all know that here. So this is one of my usual slides, but everybody here knows this one pretty well. I think that this is the thing that maybe not everyone here will know, is that if you want to follow up gravitational waves, which maybe all of you do in some sense, and a lot of you are, right? This is the timescales for release. There are now pipelines in place in low latency that can detect order 5 to 10 seconds before the merger and release GCN, or early warning signal on that scale. And then the first preliminary alerts are still out here around 30 seconds. They're getting better. I don't work on that part, but I want to put a plug for them, because the people who work on this work extremely hard to get these announcements out very fast. So if you want to follow those up, you should be subscribed to those. And then our database that hosts all those is Grace2B. And like I was saying earlier, no, that's terrestrial, but anyway, the sky maps have been getting better as Virgo is getting more sensitive, right? So the sky maps are getting much more reduced. But compared to the sky maps you guys are used to, we're talking not even close. Like, you know, the scales of what you're talking about is a bad localization is very precise as far as we're concerned. Okay, so formation mechanisms, you heard about those just now, so I'm not going to spend a lot of time on that, but where does the FRB happen in these possible scenarios, right? And what's the time scale? That's why I asked the question there. So it's great for me to hear that, because we have to worry a lot about that time scale from when the merger happens to the FRB. But there's the other half, which is the nice thing. Here's the merger one, right? Compact binary coalescence, which allows a modeled search, which is much more sensitive. But we also still do our gravitational wave burst search, which is the unmodeled search. And we can do that for things that are magnetar flares, for example. So we can do both, and we do both. It's all about timescales and false alarm rates, really, that matter. So of course, magnetards are the origins of some bursts. I have this in here just as background. But then there's some assumptions we have to make. Okay, so to do our search at all, we have to make assumptions. You can just compare the volumetric rate. This is all from before our paper was produced, our 3A paper, right? So this is going to be a little bit out of date now. But basically, the neutron star rate, the inferred merger rate for neutron stars is like 1,700 per gigaparsec cube per year for binary neutron stars, and then it's about 140 per, maybe 10 to 140 per gigaparsec cube per year for neutron star black holes, right? And that rate's big, and so that means like that's bad in some way. The FRB rate's also big, right? So something on the same in the same unit, something like that's a little old, but something like 3.5 times 10 to the 40 gigaparsecs per year. But that's a lot bigger than the other rate, right? So this, just comparing the rates, that means the the binary neutron stars could just be at most 15% of the FRBs, and the neutron star black holes would be at most 1%. If these rates were right. But thankfully these rates are still changing, which makes me still happy. As long as those rates aren't lock solid, then I'm happy. But yeah, so we can still have a chance to look for these. We have to assume then that there's some subpopulation if we're going to do this compact binary coalescence search. And I think we can make that. We've heard here a lot that there's likely more than one population. That was the discussion session at the end of the first day, right? There's likely more than one population. So I think we're okay to do that still. I think it's worthwhile. And I think in particular that paper, the one that talked about the 25 repeating faster rate sources, really pointed out that there's some statistically significant difference. It seems like the non-repeaters are further away, which means harder for us to detect, right? So that's the other problem with that. Okay, so targeted searches. Okay, so why is it targeted? So what we actually do different than what we call our all-sky searches, which are our low latency searches that you would get announcements from. We follow these up with additional deeper searches. First, we use the time, and the time allows for a more costly search to be run, because we're only going to run it on these specific events. So we use a more costly search, and it's a search that actually takes much more computational resources. Second is that we're assuming they're electromagnetically bright, that's EM bright. We use a reduced set of possible gravitational waveforms. So we don't have to search all our templates of all our black holes, right, all our binary black holes. So we can throw all that out. Actually, saves on computational resources on the other side. Next, sky maps. So the sky map says we have a big reduction in our background, actually, right? By having the background of all the sky triggers from all sky, and if you go back to what I was talking about before, there's glitches. Those glitches are at random times, and we're shifting 2 detectors worth of data against each other, so you get random overlaps between the glitches that then look like possible detections, right? But if we have a smaller shift, which means we have fewer points on the sky where we're allowed to shift the times, that's a much reduced background, which is actually really good for this search. And again, nominally you would see all sky movies down slightly. Okay, and again, we can also do things with coherence if the data is clean enough to do coherence on it, and specifically with 3 detectors is best, but 3 detectors are great. Okay, anything else? Yeah, nothing else there. Okay, so here's the two searches. The coherent search is using this pipeline called PyGRB. It uses the template banks of expected waveforms. The search window, this is what I was asking about that too, is just from the external event. We look minus 10 seconds and plus 2 seconds. So that's from the FRB. And that's kind of a limit with the pipeline we were using, because if we go beyond that, the sensitivity gets so low that we might as well not run it. But the pipeline has been rewritten and is currently being reviewed. So we might be able to go further with that. But then it's a balance between having a wider window means lower sensitivity, et cetera, right? So we have to play that balancing game. Where do we hit the limit where the false alarm rate is too high? The range is 30 hertz to 1,000 hertz. The localization is using a wide grid to search over all possible FRB localizations we get. So and in this search that I'm going to talk about, it's all the chime triggers that we use. Okay, unmodeled search for gravitational waves. These are using X pipeline, and that one has a bigger window, negative 600 to plus 600 seconds. Plus 60 seconds from the fast rate burst. So much bigger window, which means it's also going to be less sensitive, but it's allowing for many more waveform models. So this kind of gives us like catch anything that's loud, right? That's the goal of this, catch anything that's loud. Again, bigger range in frequency as well. Okay, sensitivity for these is in both cases assessed using a lot of injections. So that's also the big cost to our pipelines. is we do a lot of injections to basically assess our range, our sensitivity to HRSS, and the energy of the event. And finally, localization. This can use up to 5 small grids because in the CHIME data, I don't know if you know, the initial localization is up to 5 small spots, right? So we can use all that in the second one. The first one just uses a wide grid to cover it all, just because it can. And then finally, there's a rate of search, which we'll go back to. Okay.
Yep, done.
Good. Okay, lower limits. Okay, so this is then with all those injections, right? This is saying how far in the universe could we see, assuming we put in injections that are reasonable. So this is then, if you look at this, about 100 megaparsecs here, 200 here, 300 here, and this is just a cumulative histogram across the events we analyzed. This is for the O3A search. And this is the binary neutron star, or a generic neutron star black hole, or a line spin neutron star black hole. So we're most sensitive to the line spin neutron star black hole, right? Some of these are getting out to 100, 200, 300, 400 megaparsecs. So it's, if you compare that to what I said before, 160 megaparsecs, you can see that this can go much deeper if you have the right waveform and that you're lucky. So it's very good for that. Exclusion distance for the generic burst search though is smaller. This is 10, again, 20, 30, 40. Some go out to maybe 70, so that's about the limit, 70 megaparsecs. And then we also just check for any background, like an overall background across the entire search. I like this plot just to show you a sense of distances. So these are, again, the CBC search with the neutron stars or the neutron star black hole. And so the inferred distance from the dispersion measure is the box and whisker, so the black box and whisker. So that's where the FRB should be relative to this. And then that's our exclusion distance because we had no detections in our O3, right? So that shows you that maybe we're getting close, but this is 90%, 90%. So there's still some range in there for that first one where it could have been a neutron star black hole and we wouldn't have seen it even though it did produce. Right? There's still a possibility. But you can see that this is O3A data. Of course, in O4, this should be much, much better, right? So that's the idea. And there's still a 3B to be produced. Okay, and then the other thing is from the burst side. Okay, we can use the burst searches and assume some amount of energy is released. But instead, you can go the other way around and put an upper limit on the energy that's released, right? So you can say, all right, well, assume the luminosity distance is known from the FRB, and then use that to limit the energy. So this gives us our energy limits, and they're not super limiting. The best one here is 2.5 times 10 to the 50 ergs. Okay, so it's a lot, and that would be for the best one. And that's still probably an order of magnitude above the most generous model that you might expect for some of these, so it's still not that limiting yet. Okay. And then our closest repeater, that one was 10 to 55 ergs limit, so not great, but it wasn't very close for that group of triggers we were analyzing. Okay, the one I skipped over before is called Raven. This is something I'm working on now. Thanks. This is something I'm working on now for the second part of O4. We've been working on this a lot by working with the CHIME folks. And what we've been trying to do is, in real time, find coincident things, right? This is our real time, just look for things that we've detected, look for things that they've detected. We just have a technical limitation that we can't ingest the CHIME triggers in real time just yet, which we're just trying to overcome right now. Maybe for the last bit of our observing one, we will have that. If not, I'm just gonna run it on my own. Anyway, okay, so that's the plan. But that one also didn't find anything super significant to O3. So, the conclusion is I really wish we were having this conference in about 2 months from now so I can tell you the O3B results, but I'm not allowed to tell you today, but I can. So it's really unfortunate. We just haven't had it approved by our release team, our management team, which I'm also part of. But anyway, okay, so no significant evidence for gravitational waves so far. Okay, so yeah, and our limits on our energy are there, and I'd say the neatest thing is probably this, combined with the fact that we're going to be that much more sensitive in O4, that we're really going to start putting some limits on some of these, at least individual events. Still doesn't tell us about the population. Next.
Most of the, if not all, most of the merger scenarios proposed for FRB emissions involve FRB emission coming along the binary plane or perpendicular.
Yeah, okay.
So having this prior knowledge, does that help with an improved sensitivity in your search for gravitational-wave counterparts?
The sensitivity to the different inclinations varies, but it's not, we're not that, because we have two detectors and because of the location and because of the polarizations, we're not that insensitive to anything in particular. I think that's the right way to answer your question. I don't think it varies our result that much. And when we do the injections, we're doing a pretty big span across all inclination angles of the orbit and face on and everything. So we cover that in the injections pretty well to say, yeah, I think we're not very limited by that. It's something I have to think a little harder about though. Good get back to.
Any other questions for Ryan?
Yep.
Well, I'm just trying to read what you meant or could mean when you said that you're not allowed to say something for 2 months. Usually that sentence means that there is a positive
I'm not allowed to say anything. No, we've been working very hard on that analysis for a while.
Could you wink? You don't have to say anything.
I don't think I'm allowed to. No, I'm not allowed to. No, I'll say this. One thing that we're spending a lot of time on, and this has been in our white paper for a year and a half now for a reason, that we're working very hard on making sure we have a way of estimating false alarm rates for everything, right? Very, very carefully. So that's kind of the biggest thing we have to worry about, making sure that our false alarm rates for anything for multi-messenger is lower. And so that kind of, I didn't have enough time, but they asked me to do one question for 3 to 5 years. It's really that one. Is if there's any way to reduce the sample, right, reduce the number of events over which we look, like you were saying actually before about maybe the inclination angle or something like that, then we can maybe lower our false alarm rate of combinations. Because LIGO sky maps are big, you're going to get, like I think Ignacio was going to talk about that one before, you're going to get some things that just seem to overlap, right, at some point. So you have to be very careful to make sure you get that analysis correct. So that's the big hard work at the end, to be very careful. I hope I avoided your question accurately.
I can ask this question now. We have this interesting talk where they said that it's possible that FRB actually happened even 100 or 10,000 seconds before, I don't know. Elias, what number you have in mind for the pre-merger scenario?
For the really one that's far out.
Yes.
Yeah, I thought the dispersion delay is like minutes or so. So the problem is that the further you go out, right? Like it depends on the frequencies. I mean, the ones that are further out also, I think, will be outside of the chime band potentially, right?
I think the models would be
400 megahertz.
right.
Yeah,
If the
so-
gravitational wave is thousands or more seconds above, it's the model where you've already merged. You have a magnitude of 4 and then you
No, I'm actually saying that FRB happens before.
Oh yeah.
Because that's the first thing you said. It's the easiest one. You
Yeah.
have the environment which is less constraining. So now is it possible for you to go back to 10,000 seconds before?
Again, if you do that, you get many false alarms. You have to have a very loud event. That's the truth, right? And right now we're working on the edge of our sensitivity, right? That's the whole trick. So yeah.
So the thing is, many of your simulations, they don't produce FRBs several minutes before the merger.
No. I think several minutes before the merger is your model. Like the
Yours-
stuff that we have investigated is like
Yeah.
seconds to milliseconds. before
Exactly.
merger.
Yeah.
So what we have is pretty much
Yeah, no, I'm talking
within
about the one
within
that
range.
is saying that even that the pulsar magnetosphere or black hole
Yeah.
can actually produce FRBs
Yeah.
and then it merges. So it's like 10,000 or more like seconds before actual merger happens, right? If I vaguely remember your slide. There are 1, 2, 3, 4.
Yeah, exactly. So the top one, I think the most likely one is either you have some sort of wind interaction that Bing has done, or if it's what Naveen has done in terms of driving something out. The interaction between the two stars, that's something, just if you think in terms of scaling with separation orbital frequency, the power is very high. It's somewhere between 3 and 7. So you get very strong suppression if they're further apart. So that only works out. Most of these models, if you're very, very close.
I see. You don't need to increase the window then. 200 is a good bet. Seconds, right?
Yeah, well, I mean, it's minus 600 plus 60, so
Sorry,
There are certain models for the crush shattering of magnetars with the pre-merger emission. That can happen minutes before called resonant cross-shattering. It has to be a resonance with the orbit.
But that resonance is at 100 hertz.
Yeah.
The interface mode. So that's actually not so bad in terms of that time scale. Like we did the estimate.
Okay.
The major constraint also comes from if you actually want to have that whatever wave you emit undergoes nonlinearity. That sets another
Okay.
sort of limit.